Okay, so welcome everyone to this lecture on some examples of dynamical systems applied to biological problems. In this series of examples, we're going to take a look at particular problems in mathematical oncology. Right? So we're going to develop very simple models that apply to different therapy scenarios for mathematical oncology, for cancer cells, and how to deal with them. And the important aspect that we want to remark out of this is how dynamical models, these ordinary differential equation models that we work with, actually teach us a lot about certain qualitative aspects that otherwise would sneak under the rug, right? So if we pay attention to these specific problems from the mathematical standpoint, we actually gain way more insight than if we wouldn't. Okay, so to start with, we're going to start with an example with using oncolytic viruses to treat some cancer tissue. In doing so, we will consider the following scheme. So consider there are some cancer cells in our system, and these cancer cells are fed at a constant rate that we call it mu. Right? So this is going to be part of already our differential equation. We can also consider that these cancer cells are being depleted by some natural decay rate at effective rate delta. And now we are going to introduce a virus that could be, for example, a synthetic virus that acts as an oncolytic agent. This means that it'll somehow inhibit these cancer cells. So consider there's this compartment that we can call it the viral compartment, and it's basically inhibiting these cancer cells at some efficiency epsilon. Right? So this is a very simple setup that we can start now to prod and understand from a mathematical perspective. And let us do so, as we have learned, which is by introducing ordinary differential equations that model these dynamics. Because we are focusing on cancer cells as our target, we can start looking at the ordinary differential equation that governs this system. Notice that for simplification issues, we are going to consider the following, which is that the viral load that we're introducing into the system, this synthetic oncolytic virus, is going to be considered as a constant. Because there's a natural introductory rate for cancer cells, so there's this rate at which I'm introducing cancer cells into the system, which is considered to be constant, we can also consider the following situation in which the initial conditions, namely the initial number of cancer cells, can be taken to be 0. And we are going to take these conditions along the whole problem. Now let us start by working out the ordinary differential equation that is governing this system. We can start by the first term that we discussed, which is this mu rate of introduction of cancer cells, taken to be a constant, so it has to be something that looks exactly like this. Now consider next the decay rate. Decay rates have to be negative because basically we are depleting the number of cells. It goes with this efficiency rate, but it also is coupled to the actual number of cells that are in the system. So therefore, there must be here this variable c. And finally, we can now consider the inhibitory effect of the virus therapy, which must come as well with a minus sign, precisely because it's an inhibitory term, which is efficiency, and now the pairwise coupling between the cancer cells and the viral particles that must encounter in order to produce this inhibition. So with this, we have now all the tools that we need in order to solve this problem. And the first thing that we are going to do is we're going to solve for the whole problem over time. So we're going to find what is the actual number of cells over time. If you want, this is called the general solution of the system. To work this out, the first thing that I'm going to do is I'm going to take common factor c over here just for simplification purposes. And we can do this because precisely we have assumed that the viral content of the system can be taken to be constant, which is a strong approximation, but it'll at least allow us to solve this problem quite easily. So nothing magic happening here, and now we turn to our good old variable separation method in order to solve this ordinary differential equation. Remember, so we keep on the left-hand side, we keep all the aspects that are related to the variable c, which is our target variable or the function that we want to find. So we must take this down into the denominator. And then on the right-hand side, we're just going to stick with all the variable that corresponds to time in this case. At this point, all that I'm left to do is to integrate out on each side. So here I'm going to integrate from 0 to t. I'm going to use mute indices. And on the left-hand side, I need to integrate from the initial condition to my actual goal variable here, which is the function of the number of cancer cells over time. Now the initial condition, as we have selected, is going to be just 0. All right, so I'm going to move a bit faster here than usual, because we have seen already these integrals before, and we must quickly observe that this is nothing else but the logarithm function with some pre-constants out there that we can write down. Right? These are going to be constants that come out from the integration process. And straightforwardly, we can work out what's going to be the primitive and already work out the Barrow law for this primitive. This is going to be what corresponds to the upper bound. So here is our variable that we want to find. And then in the lower bound, we're going to have something similar, but now we have to substitute c for 0, which leaves us with this simple factor. Okay? On the right-hand side, we simply have t as an outcome of this simple integral. Great. So now we can move on straightforwardly to the actual final solution for this problem, and I'm going to do that over there. This part, I encourage you to do it by yourself, so it's a very simple algebraic process, but it's very important that we are able to do this without, with a blink of an eye, if you want. So we need practice in order to get these skills ourselves, right? So, but here, allow me to just take this and digest it quickly. Very broadly, what I'm going to do is just, I'm going to take this to the right-hand side, and then I'm going to exponentiate, right? And finally, I'm going to isolate for this variable here. Okay. When I'm done with that, I should be left with this solution. Okay. This is one part of it, and then out of the exponentiation process that I just mentioned, we shall also see this term. So great, this is our solution, and we can start trying to understand it a little bit further, rather than just writing it and getting along with it. So for example, what we can do to start with is we can sketch this solution. Here would be the variable time in the x-axis, and the y-axis I could write the number of cancer cells over time, okay? And if we notice, we will start with time equals 0. For all these factors here, that's going to give me a 1, therefore there's going to be 0, and that is natural because the initial condition that we have imposed was that the system was set up in a way that at time equals 0 there was no cancer cells, right? So now this equation moves onwards over time, and therefore we're going to do something like this, and we're going to go to some saturation point, okay? Now, this is interesting. We can actually find this saturation point. Let's call it suggestively already, let's call it C star, and let's actually compute it just as a limit of this function over here. So if we take the limit for t to infinity, that means we are taking the large time limit for the particular solution that we found. Quite simply, we'll see that what happens is that this term over here, now it's exponentiated to something that carries a minus sign with it, and it exponentiates with a very large argument, right? With a minus sign on top. This means that this is going to go to 0, this is going to vanish eventually, right? And all we are going to be left with is this part over here. So I'm going to write it down. Okay? So this is going to be our asymptotic value for the number of cancer cells for this particular therapy where we are using synthetic oncolytic viruses. Could we actually reach this, this statement without going through the whole ordeal of solving the equation? Well, the answer is yes. All we need to do is pay attention to our model that we initially wrote over here. Right? So here we had that the rate or the derivative at which c was growing was given by this. Therefore, if I am now thinking that there must be some equilibrium point at sufficiently long times, this shall correspond to actually making this derivative equal 0, right? Because what's going to happen is that this is going to behave like an equilibrium fixed state or fixed point. Therefore, if I take this derivative to be 0, let's do it over here. So if I'm looking for this fixed point, all I need to do is take the derivative equals 0, which very simply, you see, if I take all of these equals to 0, that's going to give rise to mu over all of these on the denominator. Right? Which is exactly what we got over here. By thinking and previously solving all of the system, we actually reached the same conclusion. Finally, I want to comment on something that I will leave as an exercise, which is the following, and I'm going to write it over here. Like, now, focusing on the actual general solution that we got for C, I would like to ask the following. So, if we are looking for a particular fraction of the number of cells from this C sub infinite or C star, whatever you want to call it, total number of cells, we can ask the following question. So consider some time, we're going to call it T sub f, which is defined such that the total number of cells at that particular time is going to be a fraction. Here f is a number that is smaller or equal to 1, depending on, it's better to just keep it smaller than 1, times C star, or C when we are waiting sufficiently long times, right? So this is something that it's very, it's widely used in very different scenarios for dynamical systems. For example, when we want to know if a decay system, how long it'll take for it to go to the half of the initial condition. We are not doing that exactly here. We are asking how much time should I wait until I get a fraction of this final or this equilibrium state, right? And the question I want you to solve is to find precisely this T of f, which is a function of f, to be redundant, right? So I would like you to do this. I'll give you the solution, but I encourage you all to do it at home on your own and find that this is precisely this value over here. Notice that there is going to be a minus sign in this expression, but that shouldn't surprise me very much because there's also a logarithm with a 1 minus f, and as we said, f is less than 1, so this is going to be well defined, but it's going to be a negative number, right? So all that I leave you as an exercise is to solve this particular equation. All right, let's move on with our next example. In this case, we're going to talk about a theoretical proposal that actually sheds light into something really interesting that happens, and we will have time to explain it accurately and observe how, for this particular example, which we are going to define now and we are going to call it cancer cell fusion therapy, dynamical systems approach, it actually is the key in order to understand how this could at all be a good therapy in general, right? And we will see why step by step. So consider in this case that we have some cancer cells, all right? And now suppose that they are replicating at some fixed rate. So this is a replication rate now. We're calling it mu, but this is different from before. This is a replication rate. Now consider that we are trying to induce some inhibition for this cancer via some chemotherapy process, which is just a drug that we inject into the system, we include into the system, and this drug at it kind of acts with a given fixed rate eta, and it inhibits the cancer cells C. So that's pretty straightforward, but now we are going to introduce yet another combined therapy which allows for the following. This could be thought of as a specific pharmacological drug that facilitates the fusion of the membrane of two cancer cells, and therefore they fuse together. So basically what we are thinking in terms of a dynamical systems approach, in sort of a diagram over here, is that this drug is going to promote the following process. So we take now a given cancer cell, another cancer cell, and now when they are coming together, they fuse in a sort of a hybrid of two cancer cells altogether, but that can trigger apoptosis in this case. And that's the whole idea behind this process. When two cancer cells fuse together, there's also a lot of errors that can occur, and some of the metabolic and biomolecular pathways can trigger apoptosis. So therefore, after this pairwise interaction, what we shall see is that this goes to zero, right? So we are going to combine two different therapies. Again, one is simple chemotherapy, and the other is this therapy that promotes cancer fusion. All right, so let's see how this shall work from the mathematical standpoint. What should we expect to see here? First off, let's start with our ordinary differential equation. And, well, we have a replication rate. So if we have a replication rate, this means that cancer cells in general are going to be replicating at rate mu. This, we know, is the precursor of exponential growth. But then there's something else also in the system, which is eta, which corresponds to this inhibiting drug that we include into the system in order to basically inhibit cancer cells. This is going to be of this form. It just takes cancer cells, and when they interact with the drug, they just are depleted. Okay, so far so good. We understand this process. We have seen this before. But now we introduce this novelty that it's, again, part of a proposal, a theoretical proposal, which works as following. If we have this corresponding drug that allows for cancer fusion, what we shall see is that there's going to be an interaction between pairs of cancer cells, right? So pairs of cancer cells must encounter in order for this interaction to happen. So we are going to have, for starters, we're going to have this this nonlinear term, and that's really a big part of this problem. The fact that we are introducing nonlinear terms via this specific biomolecular pathway of fusion of cancer cells. Again, these are going to end up disappearing via this process, right? So this is, as a matter of fact, another inhibitory term, and therefore it will come with a minus sign because it's actually depleting population of cancer cells. But how many cells is this process depleting? So every time that I get a pair of cancer cells, both of them are going to coalesce, they're going to come together, and then they're going to disappear together, right? Because apoptosis is going to be triggered in this now sort of amorphous double cell, and therefore both of these initial cells that we had in the beginning are going to be depleted out of the system. This means that here I have a factor 2. Every time that this interaction occurs, I lose 2 cancer cells. But obviously we have to also include the efficiency at which this is occurring, and that of course will depend on a number of factors, including the quality of this drug that promotes this sort of phenomenon. Great! Now we have our ordinary differential equation, and we can start working out some of the features that we all know and love. In this case, what we're going to do is we're going to not solve the number of cancer cells over time, but just go straightforwardly trying to understand what's the equilibrium or the fixed point situation that we shall have from this system. Remember, so when we want to find equilibrium points, what we have to do is we're going to take the derivative of c over t equals 0. Why? Well, remember that basically what this is telling us is we are going to look for specific solutions of the number of cancer cells that are fixed in time in the sense that they do not change, right? And we're going to see whether those solutions are stable or not. Let's go step by step. First off, I need to figure out what this equation is telling me. So very simply, I can take C as an overall factor, because there's one C here, there's one C here, there's one C here. Here there's actually two, so there's going to be one remaining. And I'm going to write it like this. There's going to be mu minus eta. This term is this term over here. Okay, minus 2 epsilon C. And basically what I'm trying to impose by looking at the different fixed points is to impose this equation. Very simply, this equation gives rise to two solutions of the fixed point equation, which is trivially C sub 0 star, basically no cancer cells. And there's another state, which is C equals mu minus eta divided by 2 epsilon. So we're going to call it C1, and it's very simply the 0 that it's sitting right here, which I can write like this. Right? So we have found two fixed points. Great. But now we, of course, need to know whether any of these fixed points, how do they stabilities relate to each other, right? We have a certain bag of tricks in order to do so. So let's just apply them now. Very simply what I can do, and let's use this method for now, is I'm going to use the Lyapunov coefficients. And remember, this works as follows. We need to take this function, right, which is a function of C. Let's write it over here. This is a function of C, right? And I need to take the derivative of this function of C over C. So let's write it like this. We're going to use the Lyapunov coefficient for this particular fixed point. So I'm already writing this here. This is what we're looking for. And how do we compute this? Well, simply we take the derivative of this function f of C over C, right? And we substitute at this specific fixed point, which is what often is called the trivial fixed point. Not always, it's not always there, but in this case it is, which is when it corresponds to C equals 0, or whatever variable you have equals 0, that's usually called the trivial fixed point. Okay, so is it very hard to work out this derivative? Well, no, it isn't, right? So first off, we have this term over here, which is going to stick around, mu minus eta. And then there's going to be another term over here which carries a 2, therefore there's going to be a 4 going down, right? So we are going to have, verbally only, we're going to have minus 4 epsilon C. But because we are studying this at specifically this fixed point value, the trivial fixed point, whatever terms that are left with carrying a C are going to vanish when I study this fixed point. And very quickly, I could write down this as a solution, right? Interesting. So this is our Lyapunov coefficient. And we now need to look at, well, its positivity or its negativity. Is it positive? Is it negative? But notice that what we have been left with here is a subtraction. Therefore, there will be two potential states here, two potential regimes, if you want. So in one regime, if mu is larger than eta, what we know is that this particular fixed point will carry a Lyapunov coefficient that it's larger than 0, therefore will be unstable. Right? Whereas for mu less than eta, this particular fixed point will carry a Lyapunov exponent that it's actually negative, meaning that it's an attractor, and therefore this is going to be a stable fixed point. And behold the trick that we shall be using all the time. We are working in one-dimensional dynamical systems, right? Therefore, I could be drawing the following situation here. I could be thinking of, okay, so here is my C sub 0, right? And this is the real line, okay, which basically is characterizing all the values of the total number of cancer cells for this specific dynamical system. Okay, consider one of the regimes. Let's call this this regime over here. Right? So if we consider this regime, what we are seeing is that this is an unstable fixed point. And if mu is larger than eta, when we go back to our second fixed point, which is this C1 star, this is going to lead us to something on the numerator that it's larger than 0, in this case mu minus eta in general, divided by 2 epsilon. but this is a positive number, right? So this is going to be sitting somewhere over here. I'm sorry, this is 1, right? But we have already stated that in this particular regime, right, which I'm highlighting over here, in this particular regime, we know that this is an unstable fixed point. Therefore, there must be a flow, right, from this unstable fixed point to the stable one. And in virtue of the fact that there's only this other point here, this must be the other fixed point, and it must be stable. And that's a topological constraint that only occurs in one-dimensional or one-variable dynamical systems, right? When we are moving beyond that, we need to tread lightly. So we have already this prediction that we have obtained, not by looking at specifically the stable or unstable properties of the one fixed point, but actually looking at the zeroth one, namely the trivial one. But this allows us to just move from one solution to the other, and this is a way of doing this a bit quicker than usual. So I don't need to go and compute the Lyapunov coefficients now for the other fixed point. I already know in virtue of this one. Very directly, and I'm writing this like this is going to be a non-physical solution, right? And maybe here I went too fast, but the idea is that when I have the situation at which actually eta is larger than mu, what I have is this is a fixed point, but now if I look at C1, because mu is smaller than eta, this is going to lead us to a negative value, which doesn't make physical sense, right? A negative value on the number of cancer cells of a system should not be a proper solution of the system. And it shall sit over here in this diagram, right? But this is sitting here on the non-realistic solutions. Yet the actual stable state is actually C0 star. This is not an unstable state, and it actually beyond that, it's not even a physical state. It's just a mathematical solution, but it doesn't apply to our system, right? So this is something that we will see very often in all of these problems. But I want to make a specific emphasis. We shall never see a solution that should be stable that it goes to the negative. So if that happens, this means that we might have made a mistake along the way. So we know that now, thanks to this diagram over here, when this holds, C0 is going to be unstable, and we can also say that C1 is going to be stable. On the other hand, if we are under this regime, we also know that C1 is going to be unstable. And moreover, we have also argued that this is going to be a negative value, and it'll lack any physical sense. So it's non-physical. Okay? So far we have categorized this, and now we're going to go a little bit beyond. We're going to depict something that we call the phase diagram. We're going to explain this a little bit, and we're going to move also to explain the potential function of this dynamical system, which is going to tell us a lot about the importance of precisely what we have been talking about, which is this second order term. Well, so far we have achieved the following, right? We know that for this specific regime where mu is larger than eta, we have that the 0 is unstable, and therefore the stable point will be C sub 1, which we have here written down. And again, for mu less than eta, what we have is that actually the no cancer state is the stable one, right? And the other is just an unstable and non-physical point, which is sitting there in the mathematical perspective, but nothing else. So at this stage, it is really interesting to just try to work out the potential function of this system, which we have discussed previously in these lectures. But for our particular problem now, we need to again focus our attention on the ordinary differential equation that governs our system, right? So remember, we have worked this out already. We have the derivative of C over T is carrying all of these different terms that come out from the different interactions we had. Growth, simple chemotherapy, and then this specific drug treatment that fuses cells and therefore gives rise to this second order term. Remember, our definition for a potential is none other than minus the primitive right, of this function fc that we write here in general, right? Okay? So in this case, we must integrate this out, and we are left with the following. Remember, there's going to be a minus sign that it's being carried over here, so we must remember it. So this is minus this divided by 2, and then c squared. So we have a parabola here with a minus sign that's going to change the sign depending on the regime that we're sitting in, right? Because we see here that our term that distinguishes between one regime and the other, from the fixed state point perspective before, it's sitting right over here. There's another term here which has a minus sign that we have to be very careful with, because there's a minus sign in front of the computation for the potential function, which gives us to a plus sign. And it carries a c squared. When we are integrating this, it's going to give rise to a third order term, and we'll have something like this. So now we have our potential function, and now it's time to draw it. But of course, since this is going to depend on the two regimes that we have encountered before, we must draw two different potential functions, one per each of the regimes. Let's just do it. Let's just try to work it out. Let's do it up here. Let's actually use a little bit more space. Okay. Now consider the following. Suppose that we are in the regime that we have denoted up here, where mu is larger than eta. So in this regime, we knew, right, that the stable state, the actual fixed point that wasn't a stable state, was c sub 1, right? Okay, let's see how this translates over here. First off, if mu is larger than eta, let's read out from our potential function. Mu larger than eta means that this term here is positive, which means that overall this term is going to be negative because of the negative term that is carried from the integration, right, for the potential function. This is therefore a parabola which horns are pointing downwards, okay? So we could think of, there's going to be like some sort of a parabola over here. And that's actually the leading order term, because the lowest order term for c is basically this c squared. Therefore, this parabola will be the first thing that we encounter as we are drawing this around the zero value for c as a variable. Right? The next order, and the last one in this case, it's a third order. So this is going to pick up relevance as we move beyond zero. That's the way that we should draw and think about these potential functions, right? Because this is speaking momentum as I move forward, I need to be very wary of what sign it carries. Oh, it carries a positive sign, and it does carry a positive sign importantly now, regardless of what state I'm going to be working with. So in this case, we had mu larger than eta, and that changes this sign, but it doesn't even affect this sign. This means that any time that I'm plotting this potential function, I know that I'll have a strong behavior for the third order term when we move beyond the zero. So mentally, and I'm doing this step by step now, but this is something that we have to be doing very quickly ourselves. I know that for this particular regime, I'll have an inverse parabola that looks like this. And then as I move away from the zero, I know that c starts picking up, and therefore I'm going to have something that grows as a power of 3, right? This allows me to just draw the potential function like that. So again, here I'm writing the potential function, I'm drawing the potential function under these conditions. Obviously, this is non-physical, right? All what's below zero for c values shouldn't be physical. And what we have encountered here, just out of verbally exploring this function, is that here we have an unstable fixed point, right, which is just this maximum that corresponds to the peak of the vertex of this parabola. And here I'm going to have a minima that will be a stable fixed point, which corresponds to the fact that at some point this has to pick up and grow up again, in virtue of the fact that we have this third order term. Importantly, this third order term is coming from the integration from the second order term. So it's very, very relevant that we understand the role of that. And remember that this is only because we have introduced this specific therapy, right, that fuses cells, and therefore it has this pairwise interaction built in it. That's what's giving rise to this wall or potential wall over here, which eventually controls the disease and blocks it at this stage. It doesn't allow it to grow farther. And this is very, very elegant to see from the potential viewpoint, right? From potential function viewpoint. Of course, this is going to be none other than our beloved C1 star, and this is going to be, obviously, our C0 star, or our trivial fixed point, namely C equals 0. So this is something that it can be read straightforwardly from this simple function that it was just an integration out of the original model. Obviously, we need now to go further than that, and we need to also study the other regime. Remember, in this regime we had the mutation, the replication rate of the cancer cells is lower than the inhibitory aspect that it's induced by the simple chemotherapy process, right? Well, in this case, now we can go back to our potential function, and we see that the sign up here, mu minus eta, is going to be now negative. Well, negative times another negative, that's going to be a positive value, right? Which means that this leading term, which is the term that's governing our potential function next to the 0 value, this leading term looks like a parabola with its horns pointing upwards. Therefore, it must be something like this, around at the 0 value. But this term over here, it doesn't change that at all. It is not affected by the fact that we have moved from one regime to another. This term still picks up and still grows for larger C values. Therefore, where we're left with here is there's some unphysical solutions over here that I shall draw just for completeness. And then we have this growth, right, which leave us here with a single physical fixed point and stable fixed point, which is the trivial fixed point, namely no cancer. Okay, there's no cancer left. For completeness, we could work out the exercise of, okay, what would have happened if I would have taken this for negative values? This is going to give rise to something that we have already discussed, which is, okay, if I go to negative values, I know that this is over here at 0, this is governed by our now upward pointing parabola from the first term. But as I move forward over here, I know that at negative values, C is going to pick up this third order term, but because this is negative, some negative number to the power of 3 is still going to be negative. Therefore, this has to go down at some point, right? Now, let me insist on this. These are non-physical values. These are negative C values. But it's interesting to see that, as we should expect, our predicted C1 star is sitting as a maxima, because we explained already this had to be an unstable point, sitting at a maxima right here at these negative values. These are non-physical, but still everything that has been explained from the Lyapunov coefficient perspective still holds. Great, so now we have a very interesting understanding of these two states, and now it's very interesting to draw a phase diagram that basically condenses all of this information into a single picture, and maybe ponder and think a little bit about the implications of what we learn a little bit further. How do we plot phase diagrams? Well, phase diagrams work as follows. So basically you want to pick up one of the parameters of the system. In this case, we're going to pick up a parameter of the system that is really, really relevant when it comes to cancer therapies. In this case, this is the replication rate of the cancer cells, right? So the more replicative and faster it replicates a cancer, a tumor, then that should correspond to a more aggressive tumor or a more aggressive cancer, all in all, right? So as we move along this axis here, what we're exploring are more and more aggressive cancers, okay? On the other hand, our variable of interest here is the total number of cancer cells at long times, or if you want, the stationary, or better still, the stable state of the total number of cancer cells. Okay, and now what we want to draw here is what is the stable state for each of the two regimes that we shall encounter. Well, we have explained these two regimes, we have been talking about these two regimes for a while now, and they are separated by this, right? So when mu is smaller than eta, let's write here a value for eta. So we're going to be in this state over here, right? This state over here all of the values of mu smaller than this characteristical mu value, which is eta. We know that it's governed by this specific fixed point, which is stable for this regime, which is basically C sub 0, the trivial point, no cancer cells. Therefore, we can just draw it over here. We draw it in blue, and we can say this is mu smaller than eta, right? What happens though for mu larger than eta? Now, we are going to be sitting at this particular situation right now. For mu larger than eta, what we know, let's write it like here. What we know is that the governing or the actual stable fixed point is none other than C sub 1, right? Now, allow me to just rewrite C sub 1 over here, which is going to make things probably a little bit more clear. C sub 1 could be rewrote like that, right? It's exactly the same solution. But here I have mu as a parameter that I am moving onwards, right, on this x-axis. So I see that this function as a function of mu is just a simple straight line that's growing up with this slope, right? And I can just plot it now. I can just plot it over here and then specify that this is a slope of 1 over 2 epsilon, right? Which, remember, epsilon is the efficiency at which our drug that fused cancer cells together worked. Now, with this picture in hand, what we know is that for different values of mu that are larger than eta, what we have is that we're going to have different cancer cell size as well, or different numbers of cancer cells, right? So here, the tumor is growing in this way, right? And we can make, if you want, we can make predictions on how many cancer cells should there be, provided that we know the values, or there are some approximations of the values of mu, eta, and epsilon, okay? But I want to finally point something further in this specific example, which is particularly interesting, which is the following. Suppose that there was no therapy of fusion. Suppose that all you had really was the therapy that it's the usual one, that the chemotherapy which worked at efficiency eta. What would have happened in this regime over here if there was no term for the fusion part? Well, you can explore this in different ways. You could, for example, just write down the equation, remember our ordinary differential equation, get rid of the second order terms, and then you find out very quickly that for this regime, the cancer cells are growing exponentially, and therefore their stable state, if you want, it's going to be infinite. Naturally, that's not a reasonable stable state, but it's just telling us that the system will explode and the cancer cells will grow unbounded, right, if you are at this regime. But it's precisely because we are using this squared term in the ordinary differential equation that comes out from the fusion that this is going to appear. And you can think of this as a method of control for the growth of cancer. Let us also remind ourselves that cancer is itself an evolutionary disease, right? So because of the fact that it's an evolutionary disease, even if you start a treatment and you are sitting right here, right, where your chemotherapy is kind of working and it's keeping the cancer at 0, if there's still some leftover cells, this could evolve and this could be selected for more and more resistance for this particular chemotherapy, the one that comes with the eta efficiency rate. And therefore, you could be moving towards this end. And that's effectively what happens with a lot of therapies, that cancers evolve to generate resistance, and therefore you move to this side. And so if there is no other line of attack, such as this one, the fusion therapy one, then you are unfortunately going to go to exponential growth. Last but not the least, this is a very interesting, very important problem that allows us to see the importance of understanding nonlinear dynamics in this type of therapies, but as good engineers, we cannot just be content with this. We need to go beyond, and we need to bear in mind all the different intricacies and the molecular mechanisms that exist underneath these systems, right? In this particular case, we need to understand that cancer cells have a large degree of aneuploidy. This means that they can include large numbers of chromosomes, and sometimes this works against cancer cells as potential cells that are resistant to different therapies, but sometimes it works in favor because they could acquire novel innovations that allows them to escape from the usual routes of attack, right? So even though this is an interesting proposal, all of this needs to be bear in mind, right? That these sort of internal phenomena will also be occurring at the same time.